subduction of the young Juan de Fuca plate creates the arc of Cascades volcanoes. Hotspot volcanism drives the Yellowstone caldera system. Continental extension plus a northward migrating triple junction add to the complex volcanic history. To look at the development of volcanism in the Pacific Northwest, we go back 55 million years to a time prior to stretching of the continent by basin and range extension, and when Mesozoic subduction, compression, and crustal thickening had waned. At the end of the Cretaceous, the Silesia oceanic terrain created on the Farallon Plate approaches the western margin of the continent at about 55 million years. The Farallon Plate is near flat beneath the continent, and magmatism wanes. As the oceanic terrain is accreted, subduction jumps westward, and the Farallon slab fails and founders, leaving the remnant Juan de Fuca Plate offshore. The old slab peels from the overlying North American plate, starting in the north, causing a southward sweep of broadly calc-alkaline volcanism. The Cascades arc is formed with subduction of the Juan de Fuca plate and shortens in time with the northward migration of the San Andreas transform margin. In the Pacific Northwest, early Cascades volcanism produces Eocene basalts and basaltic andesites. Alkali volcanism in the forearc taps Silesia mantle. As the slab grows, the arc volcanism matures. Volcanism behind the arc is widespread and lacks a prominent subduction signature suggesting slow regional extension. The arc widens to produce abundant ignimbrites. Downwind ash accumulates to preserve a rich mammalian fossil record. A radical shift in volcanism and tectonism begins with the outburst of flood basalts at 17 million years from rapidly north migrating vents along the boundary between accreted terrains and the North American craton. The basalt outpouring is immediately followed by a pulse of silicic ignimbrites. This burst in basalt plus rhyolite volcanism is the onset or resurgence of the Yellowstone hotspot under the continent. While subduction-related volcanism persists in the Cascades arc, migration of North America across the Yellowstone plume creates a succession of calderas that become younger to the east along the Snake River Plain to reach the Yellowstone caldera. We use a cross-section of the subducting plate and hotspot interaction in which part of the Yellowstone plume head flows up the base of the ancient, thick North American plate at about 17 million years ago, resulting in the flood basalt outpouring. As the North American plate pushes west, the Yellowstone tract migrates east. As the Juan de Fuca slab steepens and rolls back, backflow and upwelling of the Pacific mantle around the receding slab simultaneously creates westward migration of silicic volcanism across southeastern Oregon. To view what was happening tectonically in map view during those 17 million years, let's again rewind volcanism to 17 million years to superimpose the simplified regional plate motion. Block faulting of the basin and range extensional province was ongoing as the Cascadia forearc rotated clockwise about a pivot point in northeastern Oregon. At about 5 million years, bimodal basalt rhyolite volcanism migrated to the edges of the basin and range province. As the Juan de Fuca plate dives beneath the North American plate, the Pacific plate is dragging the Sierra block of California, which is pushing on the Oregon Coast Range, that in turn pushes on the Washington crustal block. The stalwart Canadian mountains resist. The youngest basalts are concentrated along the trace of the older age-progressive rhyolites in the northern basin and range. In recent time, volcanism became focused on the Cascades arc, segments of which have distinct character.
1902, Mexican farmer Dionisio Pulido thought he heard thunder coming from his cornfield. However, the sound wasn't coming from the sky. The source was a large smoking crack emitting gas and ejecting rocks. This fissure would come to be known as the volcano Paracutin, and over the next 9 years, its lava and ash would cover over 200 square kilometers. But where did this new volcano come from, and what triggered its unpredictable eruption? The story of any volcano begins with magma. Often this molten rock forms in areas where ocean water is able to slip into the Earth's mantle and lower the layer's melting point. The resulting magma typically remains under the Earth's surface thanks to the delicate balance of 3 geological factors. The first is lithostatic pressure. This is the weight of the Earth's crust pushing down on the magma below. Magma pushes back with the second factor, magmastatic pressure. The battle between these forces strains the third factor, the rock strength of the Earth's crust. Usually, the rock is strong enough and heavy enough to keep the magma in place, but when this equilibrium is thrown off, the consequences can be explosive. One of the most common causes of an eruption is an increase in magmastatic pressure. Magma contains various elements and compounds, many of which are dissolved in the molten rock. At high enough concentrations, compounds like water or sulfur no longer dissolve.